right, welcome. So note that next week, possibly 2 exam times. So Tuesday is going to be exam 4. Friday is going to be the final exam time of the normal schedule for this class. So it will be 12:30 to 2:30, and it's optional.
When will we know our score from exam 4?
Hopefully very quickly.
Okay.
I'm going to help with grading, and so we're trying to get it done within a couple days. So hopefully before Thursday, and then you can decide if you want to take the exam on Friday, maybe late Thursday night. So exams are going to be in the same for both times, Tuesday and Friday. They're going to be both in the Engman lab. So same format as we've had before too, with uploading your work to the exams for credit. All right, questions underneath those? Yeah.
Is there another final exam time if there's conflict?
This does not conflict because it is the exam time of the university schedule, so there shouldn't be any time conflicts.
Okay.
So this will be the only one. What conflict do you have? Which?
Ethics.
It shouldn't conflict with, this is the standard time frame, so if that one, which ethics?
Just like every mechanical engineering ethics.
Huh.
All of them.
Okay, double check, let me know. I'm happy to talk to Deborah Mascaro and say what is going on. And see, because this is supposed to be the published time frame of this one. So let me know if there is a conflict. We'll figure it out. Otherwise, I will see you at this one. Or hopefully you don't even need to come, right? All of you are like, please let me do well. I'm happy if you don't come too, so. But I want you to come if you think you want to get a better grade and can do better. Okay, topics for this exam. So BJT transistors with and without motors in them, understanding on, partially on, and fully on, and off. And then second order circuit analysis, like we've been doing with RLC circuits. So understanding the different characteristics that you can have from them and being able to derive the equations for those. All right, any questions about the topics of what will be expected on the exams? Or on this exam? Okay.
Excuse me?
Yeah.
For the final, if we do worse on like when we're trying to retake one,
I dropped the lower of the grades.
okay, so you keep the higher one.
Yep, so if you opt to take the final and you actually do worse than your midterm grade, then I keep your midterm grade and don't count the final. So out of those two, whichever one is higher is the one that's kept. Okay. Any other questions? Yes,
So is the final like a cumulative test or is it retaking?
it's a full retake.
Okay.
So you can expect it to be the same length of time per exam, so very, very difficult to be able to take all 4 exams in 2 hours. So you'll want to opt to say, let me attempt this one, take that one, and then attempt another one.
Okay.
Yes?
How similar will the questions be to previous exams?
Very similar. So very good study is to go back and review what did you do incorrectly on those exams. Different problems, but concepts will be the same. So it might be worded a slightly different, but as far as the level of them will be very similar. So now all of you can go back to that exam 1 and go, oh, this is so much easier now. All right, any other questions, comments, concerns? Okay, so we're going to go back and review a little bit about the transistor. So one thing to note is identifying the transistor, so identifying NPN and PNP. So identification is going to be based on where the arrow is. Is it going out or is it going in? And that will determine if it's NPN or PNP. Going out is NPN. Going in is PNP. If I have an NPN, I need to understand and know that I have a collector, base, and emitter. So I have 3 terminals for this device. Current flows in an NPN from the collector into the emitter, and I also have current that comes in at the base. For an NPN, it's opposite, and its current flow goes from emitter to collector and then out at the base. So these characteristics are ones that, or at least the way I remember which way they are, is looking at the arrow helps me determine which direction are my current flows. So the arrow I have to memorize is on the emitter side for either one. So that helps me determine the emitter. You can see that the arrow going into the PNP makes it look like the current is going to flow down from that emitter into the collector, so that's how I remember which direction it's flowing, and it also kind of looks like it goes out a little bit to the base. So that's how I remember which direction does the current flow for these. Same thing on this one, you can see that the arrow is going down this direction, so therefore the current flows down into the emitter side, which means it comes into the base to go down there. So that arrow is a big key and way to remember what way is the current flow, what type of transistor do I have, and what location do I have for that transistor, because it's on the emitter side. Does that help with how to maybe connect, how to remember those? Okay. All right, so regions of operation. So cutoff is off. This is when your base to emitter voltage is less than 0.7. In this state, no current flows, all the currents are 0. And you just look at the voltage that are on each side of those. Your check then is to look at your voltage at your base, your voltage at your emitter, subtract them and see is it less than 0.7, and that's your check. Okay, then you have 2 states of on, one where you're partially on and then one where we're considered fully on. Both of these will have that VBE is 0.7. And when we are in the partially on state or active mode, we can use that relationship with beta. So we first find one of the IB or IE first, and then we can relate IC to it. So one thing you need to remember for this solution is to take a loop from your base to emitter or emitter to base. And this is how you're going to solve for IB or IE. So that is the key to solving when you have a partially on circuit. For fully on, it's going to be, again, VB is 0.7. Oh, one back up. Checking this, you're going to check that VC is greater than VB for an NPN, and then VC is less than VB for PNP. As you've seen from all the examples, majority of them we've done NPN. So focus on that one for the exam. Okay, saturation or digital, which is fully on. So again, on state, and then we consider fully on. Here you're going to use a summation of your currents, IB plus IC equals that IE, plus VCE equals, it will either be given or you can default it to 0.2, and use both of those to solve for this circuit. Note you cannot use the IC is equal to beta IB is equal to beta beta over beta plus 1, IEE. This one is only valid for active. So that partially on is when you can use that relationship. Otherwise, we have to use a summation, and we use that the voltage drop between the collector and the emitter is that 0.2 or whatever value it's stated to be. The check for this, you have two checks. One check is going to be that you find beta forced and check that it is less than what that normal beta is that you expect. The other check is that VC is typically less than VB for an NPN. And I say typically because if you find that your beta forced is really low, but your VC is very close to VB, you're still going to be in that fully on state. So there's a few little exceptions, and that's why I just say typically. But that's also another kind of check is like, well, my VC is less than VB. Most likely I'm going to be in that fully on state. That make sense? Okay. All right, here was the summary of kind of solving the DC circuits. So you're going to make an assumption, active or saturated. So these are both on. So you assume on. And then you're going to kind of pick them. Saturation mode was lowest power consumption. And so when you're working with a motor, especially, you're going to try and always make this fully on if you can, because that gave you the lowest power consumption. All right, the next step, if you assume that you're on, then you have VBE is 0.7 for an NPN. And then you're going to if you're assuming active, you're going to solve from base to emitter, a loop, and then use the active condition. And if you're in saturation, you're going to still do base to emitter loop. And that will give you IB or IE. Then you're going to use the current summation and VCE to solve for the other currents in there. Then you're going to check if NPN is active or and beta forced is less than beta for saturation. If it is either of those and that was your assumption, then you're like, great, I'm done. If it's not, then you need to make a different assumption. So it might be on, but it might not be fully on. So you then need to check the partially on. Or you can assume it's off. If you assume off, then all the currents would be 0, and you check the voltage between the base and the emitter. So in cutoff, your check is that VBE is less than 0.7. All right, questions? Does this make sense? Remember some of this? Okay. All right, so assume that the following DC values were found for an NPN BJT transistor. So you measured VC was negative 0.1, VB was negative 0.3, VE is negative 1. Is it true that this transistor is in active or partially on mode? I'm seeing some no's. Why do you say no? What's VBE? Okay, so it's just barely on, but it's equal to it, so it's on. And then what is VC compared to VB? Okay, so VB is minus 0.3. And so VC is greater than correct? Negative 0.1 is greater than negative 0.3. And so going back to this, we have that we're on, it's equal to 0.7. And we are finding that VC is greater than VB. So it's true it's on or off, or on or no. Okay, so this would be true. All right, questions on this? Okay. All right, for this one, we're given that beta is 99, VBE is 0.7, and then VTH is 6, and RTH here is 9K. And the transistor is, assuming that the transistor is partially on and in that active mode. So that is to analyze this with an active mode. I didn't put this in, I meant to, that this is representing a motor. So this 2K is actually modeling a motor that would be in here. So solve for the DC values IB, IE, IC, VB, VE, VC, and then plug your values into this. This is for the auto check, so just ignore that for now. But there's more of these online, so you can check your answers by putting them into that equation just to get an answer to do the auto check portion. Okay, so go ahead and solve this circuit, IE, IB, IC, VB, VE, VC. So to remind you, where do you want to try and solve first? Or what do you try and solve first when this is known as an active mode condition? Thank you, yes. So you're going to take that loop from the base through the emitter to solve for either IE or IC and use that relationship of the current relationship between the two. Okay? All right, go ahead and solve this for a little bit, and then we'll go through the solution. There you go.
can either go from like ground down to the bottom, or like move just on and we know it's 0.7 because
I mean, you're not gonna finish.
you could technically retake all 4 times.
Maybe you don't have it.
Tuesday. No, I'm talking. So, what are you doing? Started 6 BTs, and then I worked my way down.
So you use 6 minus IB times 9, okay?
I forgot the transistor. You saw my grade, saw that was the same question, and then you went, no, I think you're wrong. I literally got one part credit wrong in the big question. And I gave you the transfer wrong. I don't know.
Definitely not from the night.
Look, no, I clicked the wrong one.
But still, it's alright. I got that thing when you heard.
Come in and have really shaky hands. Like, I can't click on the way sorry, I got to take the face. I'm like, yeah, shit. I scored my grade. The sounds he was making, the sounds that he made do not sound.
So a couple things to note when you have assumed it's on. We're very rowdy. So when you've assumed that it's on, you know that there's a 0.7 volts between that base and the emitter. So you can that's why we take that loop between the base and the emitter. I had a question, somebody asked, well, why not take a loop from the ground up above? And that is because we do not know this voltage between the collector and the emitter. That one is an unknown one. So that's why we don't take that loop through the collector to the emitter side yet. So instead, knowing that it's in that active mode, we can use that relationship of beta IB is equal to beta over beta plus 1 IE, so that's one equation. And then we know IB is located here, and VB is here, VE is here at this location, and then going through these is IE in this direction. So you can always like write these equations in different ways. So you could write IB here to be 6 minus VB over 9K. You can write IE as VE minus 2 minus a minus 12 over 2K plus 1K. Or you can say, my VE location here is the summation of all of those voltages, so it would be a minus 12 plus IE times the summation of 2K plus 1K plus 2. Or you can just keep going until you get back to ground. So I could do a loop through VTH space to emitter and go, this would be that's ground. Label all these plus minuses. And then this location would be plus to ground is my minus. So if I go through each of these and circle all my second signs, my loop here would be a plus 6 minus IB 9K minus 0.7 minus 2 minus IE times 2K minus IE times 1K minus 12 equals 0. If you want to, this would be one set of equations that I could use VBE. So using those 4 equations, I could put that into something like Wolfram alpha and use that to solve it. Or I could do my equations with voltages. So this would be, one equation. Second equation again would be VB minus VE equals 0.7. And then my third equation could be 6 minus IB times 9K equals VB. And then my fourth equation would be the beta IB is equal to beta over beta plus 1 IE. So that could be another 4 sets of equations, again using Wolfram alpha, or we can just use this equation and then the relationship of IB to IE. So any 3 of these options are ways you could solve this.
For the purple one, number 1,
Uh-huh.
should it be plus 12, not minus 12 at the end?
It should be a minus minus 12. So it'd be minus minus 12 equals 0. So the minus and then the value of it is minus 12. So yes, plus. Thanks for catching that. So with this just being 2 equations, this is more the preferred way I do it by hand. So I would then substitute this one in and solve for IE. And then 6 minus 0.7 minus 2 plus 12. And then I would divide by these 9K over 100 plus 3K. And this then would give me my IE value. So 6 minus 0.7 minus 2 plus 12 divided by that 9,000 divided by 100 plus 3,000. And this ends up being 4.95 milliamps. From this, then I can get IB, which is just this IE over 100. So 4.95 milli over 100. Which gives me 49.5 microamps. And I can also get that IC is 99 over 100 IE. And so the 4.95 milli and so I get 4.9 milliamps. So this gives me IE, IB, and IC. And then knowing these values now, I can find VB, VE, and VC would be here. So using that equation, either my IB equation or this other one, or I could find VE first and then do the 0.7 difference. Yes?
When you plug the second equation into the first one, what did that first term, the IE equal, or IE times 9K?
So when I plugged in IB here, this is IE over 100 here. So it becomes 9K over 100 times IE.
And that's just the definition of what beta is.
So this is that relationship because I'm in active mode. All right, any other questions? Okay, so solving this now for VB, I can write that VB is plus 6 minus IB times 9K equal to VB. Or I can write it in terms of the voltages across that resistor, which would be IB is equal to 6 minus VB over 9K. And then either way, solve for VB. So 6 minus 49.5 micro. Micro is 10 to the minus 6 times 9K, which is 10,000, or whatever, 9,000, 10 to the third. And this gives 5.56 volts. And then from here, it's easier to just do VBE. Or I'll do, so using VBE, which is VB minus VE 0.7, just solving that for VE is VB minus 0.7, so 5.56 minus 0.7. So that gives me 4.85 volts. All right, questions? Any questions on these? Yes,
Are we gonna have a question like this in the test?
it could be, yes. So unit 4, no homework this week. Unit 4 practice has more of these. So unit 4 practice to get ready for the exam next week. So, and no quiz on Friday. So study for the exam instead. All right, last one to find is VC. So again, you can write this with the voltage across the current of IC. Over here. So IC, you could write it as IC equals 0 minus a minus 12 over 3K. Or this would be a plus to minus. This would be a plus to minus. So I could say a minus 3K times IC plus 12 equal to VC. Okay, I missed the minus VC here. It's like, where did my minus VC? So, and then IC was 4.9 milli. So minus, wait, I did wrong way. Yeah, minus 2.7. So is this on and active? So what do you check? So what do you have to check for active mode? VC and VB. VC was found as minus 2.7. And VB is 5.56.
So it's not.
Correct. So this would not be active. So that assumption is actually incorrect. And you could then check for saturation. So not correct assumption. Okay, questions on this? Yes.
Does this give you information as to check saturation next or off next?
So you did find it looked like VB was very possible to be 0.7. If you found like there's no way it can be 0.7, which are sometimes the case, then it's easy to go to off right away. Otherwise, yeah, you would probably check that it was fully saturated next.
If you had a difference between VC and VB of less than, no, sorry, that doesn't make sense. But, that 0.7 that you're checking, that's between VB and VE, is that what you're saying? It looked like that would be.
Yeah, so in this case, it looked like it was easy to still keep VE and VB to have 0.7. So most likely it will be on.
Okay, that makes sense.
And probably fully on and saturated. So we can go to that one next. So if we do say, okay, this is not correct, then the differences are that we no longer can use beta, so that gets rid of this equation. RIB, RIE, and our VBE will still be the same. this will no longer be valid, but these equations are still valid. Our loop here is still valid. The difference is we don't have this relationship. So this equation is valid, but not, so annoying. But this one is not valid. So now we have this equation with so these are all valid still. We just don't know the actual value here. We don't know the values here. So instead of these, you need to know one more given, which is VCE sat. And I'm going to just say VCE sat is given as 0.2 volts. So if the given. So then we add in the other equation we're going to add in for this one. Is that we can add in that let's see. Well, we use all of these equations instead. But we can add in a loop now going in this direction because we have a known value here of 0.2 volts. So now we can take a loop from the top to the bottom through that 0.7. So with that, I'm going to start at the top and I'm going to go negative, negative, plus, and then a negative, 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 and then that negative again. So this time it's IC times 2K minus IC times 1K plus 12 minus the 0.2 minus 2 minus IE 2K minus IE 1K minus, and then the value of minus 12 equals 0. And that gives me my additional equation. And in this equation, I have IC, IB, IE, so I need one more equation. So this one is new. And then the third one is the summation that IB plus IC equals IE. So the difference between the active and the saturation is that we use the VCE value, and that will give us the additional loop, and then we use that current summation. And those give us our extra equations. And then from here, I don't want to solve this one by hand, so I would then take it to Wolfram Alpha or another, or my calculator, and use that to actually solve for those values. I could also put it in a matrix form and use a matrix solution for this also. And then from there, I'm going to check so my end check in this case is that VC is less than VB. And that beta forced, which will be the value I find here for IC sat over IB, is a lot less than 99. So those would be my checks for this case. Questions on how to do this? All right, this circuit's a little easier. So this one, assume that you're on and fully saturated. And this one's gonna be a little easier to solve by hand for beta forced. So go ahead and take a minute to try to find that beta forced. And I forgot to say, this is representing modeling your motor.
It's not that bad by the way though. It's a decent one to do.
I'll show you one more.
Plus 5 equals 0.
I did. Stands variable.
Oh wait, no, that should be negative.
I guess
Yeah, different.
I go 1.2.
no. Use this exit right here. 2 miles south. 2 miles south of there. Like there is in the city. There's that. It's just like yeah. Yeah, you leave your that's BJT.
Isn't the force
Because I had a great jacket
Okay, I did just get a negative. My beta
No order that far. That was the issue. Was I did sell for now. I don't know. Might just seem cheap. It's like I had I technically have two only one actually. That's good. Yeah. And I guess you don't call it. Well, the thing is, I don't really care about it. So I get it. So it's like I really work on that. But she also should never do anything. But it's like, even with the stuff, it's like, it's still a little like, not cold. It's not really cold. The wind lifts it.
It was such a good idea.
Yeah, I just don't know what to do.
Beta force should be super less. Yeah. Beta
And so we had a part set underneath. The tarp was bigger than 10. I have to do 10, so like, that's the way I yeah, but not at night.
Because you're saying negative
Yeah.
It's not negative.
Yeah, so I'd rather top it with that.
Kind of.
Yeah, she has budget too.
I saw even myself in there. This is negative. You're solving for negative. You're solving for negative ID, so that is negative.
I have a study to this.
Even if it's like something
you have to have
generations, and then I'm like, no, it's
You have to drive out one morning.
All right, so on this one, you're already given your VE because you know that is a battery there of minus 5 volts. So that makes it easy then to say, well, VB is going to be minus 5 plus 0.7, so minus 4.3. And VC is going to be minus 5 plus 0.2 of minus 4.8. From there, you can use the drop across the resistor, so 10 on the IC side minus that minus 2.8 because you're at minus 4.8, and then you go through the battery of 2 volts, so that's a minus 2.8. So 10 minus a minus 2.8 over 10K. And then on IB side, 10 minus a minus 6.3 over 10K. Or you could write these in terms of the voltages. So this could also be written as plus 10 minus 10K IB plus 2 is equal to a minus 4.3, and solve it for IB that way. It would give you the same exact result. And then same thing over here on the VC side. You could also say it's 10 minus IC times RC of 10 minus 2 is equal to a negative 4.8. So either way, you're going to get the same equations. The key here is that you've taken the loop between IB and or the base to emitter, but you already know the emitter, so that one makes this one easier to solve by hand. And then the other key is to take that through VCE, so taking those loops. If you didn't have an easy answer for VE here, then you would have to do one more equation for the IB plus IC equals IE. And that would give you one more set of equations. And then you could solve it that way, like we just did previous example. All right, so the check on this is that beta forced is a lot less than beta. In this case, beta was 99, so yes, 0.79 is way less. So we're definitely in that saturation fully on state.
So how do we know to assume saturation? Like, how did you guess saturation?
I stated what it was. If you were to look at this, for you guys as mechanical engineers, most of the time you're going to be, I want to design this to be in saturation because you want to consume the least amount of power. So a lot of times you may be fixed with your RC value because that's going to be whatever the motor model needs to be as far as that resistance. So you're going to be stuck with that value. So then you're like, I either can increase my voltage, because what is the condition between active and saturation? It's that base voltage compared to the collector voltage, right? So VB compared to VC. So in saturation, which is what you would want, you want VC to be less than VB. And in the active, remember VC is the other, less than VB. So this would be more what you want because saturation has the least power consumption. So with that, VC is, here you can see VC is a factor of the drop from the power supply of 10 minus ICRC, and then you can change that voltage there. Or you could add more resistance. So if you added more resistance, let's see, let me write out VC again. So VC is equal to 10 minus, or we can just put it as like a known VCC minus IC times 10K. So if we want to try to move this, say it was inactive and we found it to be in active mode, what do we have? We have control over, if 10K has to be fixed because of the motor, we have control over the current and the supply voltage. If we want to decrease this to be less than VB, then we could increase the current, which also increases power.
Or you could decrease the current of IB.
And so you could decrease, well, remember it's fixed by the 0.2. So whatever your base voltage is here, and then it's 0.2 above that. So if you decrease that range, that's going to be a lower number.
But it would give you a higher beta forced, correct?
Yeah, but it's going to keep you, keep giving you, so there's kind of some trade-offs there that you have to kind of play with. So as you increase IC, you would increase beta, which moves you more towards active region. So there's kind of going to be like a little spot in there, like this is probably better. It's closer to active, but it has lower power consumption because I've increased IC. So you could play with those two parameters, decreasing your supply voltage is also going to decrease it. But a lot of times these will be about the same, so if you decrease the supply voltage, it's also going to decrease VB. And so sometimes it's more playing with that current. So you can, most of the time you can put in potentiometers in a design like this and then turn them till you're like, oh, I'm getting, like, yeah, I am seeing that VC is way lower than VB, and therefore I'm going to be in saturation. That's the easiest way to build it, is just to kind of put it on there. Huh. Okay.
So if it was inactive and you told us to go to active, is VB still negative 4.3 or would we find it to be negative 4.3?
So if it was active, we don't know what the VC is for the active mode, because we only found it, but it will be higher than negative 4.3, yeah. VC would be higher than negative 4.3. Does that make sense? Okay.
We use the 0.2 volts to calculate the power of the transistor.
So the power of this, find another one. So you can approximate the power because the biggest current here is, well, in this case, they're not actually that much different. So you would probably do both. So you would say 1.28, which was IC, here, I'll write them out first. IC times VCE sat. And then it's going to be IB times VBE.
Just add them together.
And you would add them together, yeah. So you would take that I times V for each of those and add them. And that would give you the power consumption here.
Is there a reason we don't use the IE?
So it's kind of what is going through the transistor, and so the current actually is flowing internally through the collector to the emitter, and internally from the base to the emitter. So that's why we use those two. So you use the same equation in active, but IB is usually so much smaller than IC that we usually just approximate it with IC times the voltage between the collector and the emitter, which will not be the saturated one, which that's why this is always lower, is because that VC sat is only 0.2. Here, well, this wasn't a good example, but usually, for active, VC is going to be greater than VB, and in this case, it would probably be greater than 5.56. So you're looking at about 6 volts times a milliamp, so a lot bigger than 0.2 times a milliamp. Does that make sense? So that's why that one was way lower. So this will be still lower than active mode. All right, any other questions? All right, a good refresher of some hard problems with BJTs. Okay, so Unit 4 has more examples like these that will help you prepare for the exam. There will definitely be a question on saturation and a question on active mode, so make sure you can do both analyses and that you kind of understand the basics of what we talked about here. So understand what beta forced is, how to find it, understand where and when you can use that relationship of beta, and then identifying the transistor, knowing the modes, the 3 modes, and how to check for those 3 modes and what mode you're in. Okay. All right, any other questions about BJTs before we move to the next topic? Okay, so that should be what you'll need to know for the BJTs. And then the last topic is the second order solution, and we're focusing just on the RLC solutions. So it will just be a second order solution only. So understanding when and where you can use these equations from the table. And so understanding how to identify that series or parallel configuration of them, being able to find your alpha, omega naught, and then the other variables. So your initial condition, your final condition, and being able to then identifying which equation you're going to be using as far as that final solution, and then understanding the difference between overdamped, critically damped, and underdamped. Okay, so those are the main things. So going back to these, you need to know how to convert into the frequency domain. Well, it depends. So, using the final, so let me back up. So finding, since we know these are an RLC circuit, makes your solutions a little bit easier than some of the ones I did in class before. Because with those, and you can use the technique with Laplace to do higher order solutions. But I think for now, just really focusing on the RLC. So understanding that you change this into the frequency domain, you can solve it, and then you can get out a time domain for any input signal. What we're going to focus on is just these basic DC input signals. So that's going to make this a little bit easier solution too. So with this being only a DC input signal, we can use the tables which already have done that method of moving it to the frequency domain and finding a transfer function for those. The thing you have to note though is those are only finding specific ones. So if you're in series, it's only going to find the voltage across the capacitor, and when you're in parallel, it's only going to find the current through that inductor. So from there, then you can find other variables based on that. So if I wanted to find the current, for example, in this one, IC, which is also equal to IL, then I would take C and then multiply it by the differentiation of that voltage VC. Does that make sense? You guys remember doing these? Okay. And then same thing here, if I wanted to find either, say the voltages, the voltage across the capacitor is going to be the same as the voltage across the inductor, so then I could find IL first, and then it's L, DIL, DT. So you could just differentiate it and find those time domain solutions. All right, so one of the first steps is to find, am I in series or parallel? So how do I know which one I'm in? Thank you. So look at the time, the final time, look at that circuit, and then look at the location of where your inductor and your capacitor are to each other. So in this case, looking at the final time, it looks like this is going to be open. And so what will this one be? Correct. So this one would be a series. So now I've identified it's in series, so now I need to find that alpha and that omega naught, which are going to be, remember, they're part of your characteristic equation, so they're going to help you determine your roots of your system. And the relationship between them is then going to determine what characteristic you have between that underdamped, critically damped, and overdamped. So alpha for a series is R over 2L. So this R is going to be the RTH, which is the equivalent resistance that it sees when L and C are in series. So we note a little difference with this circuit in that we have an element that is between my L and my C. How do we find the equivalent resistance then? Do you have an idea?
Yeah, you do difference of the voltage from A to B from the top and bottom, of course.
So is this the same is one question. So here we have an inductor and the resistor is in between the capacitor. What if we took this branch? So note that this is an extraordinary node here. This is an extraordinary node on the bottom, which I can put as a ground. What are the connections between each of these elements? They're ordinary nodes, right? Which means that the current flow is going to be the same through all three of those elements. Therefore, is the current flowing if I move the elements around in the branch? Are they the same current? Still going to be the same current because it's still going to be the voltages across the branches divided by all of that resistance and impedance between them. So from this, I can actually move those two elements to be next to each other and find the A to B this way. And that will include all of the resistances that it basically sees. So these are the same. So the voltage from the bottom, if that was ground, up to A is still the same, it's just a different order. So instead of having, here's another example. So if I have batteries and I place them, say I put 2 volts here, 5 volts here, and 3 volts here, my voltage here is 10 volts, right? Same current flows through each of these 3 elements. So what if instead of that, I move these, and instead of my 3 volts being on top, I move this 3 volts to be in the middle, and I move my 5 volts, and I move my 2 volts. So say I put the 2 volts in the middle, put the 5 volts on the bottom, put it on the top. So I've moved all of them around. I still have the same combination to give me 10 volts across the whole branch, and the currents through each one is the same still. So this is the same idea of moving elements within a branch. You can move the voltage source, you can move any of the impedances or the resistors around in a branch. So that makes it then easier to see that my equivalent resistance, I'm going to open up that source, and then this one is a dangling resistor. So my equivalent resistance here is just going to be the summation of both of those. So 0.1 plus 0.2, or 5.2, to give me a 0.62 ohms. Does that make sense? Okay. So now L was 0.05. So 0.62 over 2 times 0.05. And then omega naught is 1 over the square root of LC. And so 1 over the square root of L, which is 0.05, and C is given as 1 over 1.8. That's 6.24. So this gives an alpha of 6.2. Do you guys remember the units? Meters per second. Such a fun word. All right. And then this one is 6 radians per second. So what are we in? So alpha is greater than omega naught. So we're in overdamped. And our S1 and S2 depend again, the roots of this depend on that alpha and omega naught. So S1 and 2 is when you have a plus and a minus of these. So S1, we get a minus 6.2 plus the square root of 6.2 squared minus 6 squared, which gives a minus 4.64. And these are also meters per second. And S2 is minus 6.2 minus the square root of 6.2 squared minus 6 squared. And this is a minus 7.76 meters per second. So then we need IC0, VC0, V infinity, and I already did those. IC0 again. So that's going to then depend on the switch. So we're going to look at this, and with the switch at time 0 minus, it's going to be closed. So we're going to have this circuit. And you want to find the current through the inductor, IL, and the voltage across the capacitor. You assume it sat there for a long time. So do T equals 0 minus. So sitting there for a long time is going to do what to the inductor? Correct, wire. And then what happens to the capacitor?
Open.
Correct. So open for the capacitor, a wire for this one. So is there current flow here? No current flow, so 0 current there. So my IL is going to be the current going through and going down to the 0.1. These are exactly the same, so that's going to divide this evenly, so this will be 2 milliamps. If you don't see that, you can take, can find the voltage here, Vx, and say the current in this is Vx over 0.1, this one is Vx over 0.1. Sum all three of those together, and then solve for Vx, and then IL is Vx over 0.1, and it will give you the same, 2 milliamps. All right, then we know that at t equals 0 plus, IL 0 minus will equal IL of 0 plus. We also know that the voltage here is going to equal the same as 0 plus. So to find this voltage is going to be the same as finding this Vx, which we could find by just the 2 milli times 0.1. So Ohm's law. All right, we'll work on finishing this one next time, and then we'll go into some additional examples. Are there any requests for specific types of examples or concepts you want to make sure to review before more of this? Okay, we'll do more of these.